Right, welcome back. So just to refresh you what we did refresh your memory of what we did yesterday. We are trying to describe the dynamics of quantum many-body systems, and of course in our case in atomic nuclei. And we showed that the Schrödinger equation, which is what we should solve if we want to be non-relativistic. Yes. Glad to. The Schrödinger equation can be recovered from a variational principle where you require the action to be stationary. And we took the example of the Dirac action. And but of course, I mean, we show that solving the Schrödinger equation exactly for a many-body system is almost impossible, and doing it with a variational principle, doing it exactly would not help much. So what you need is to do approximations, and variational principles are useful because you can use a variational space in which a state can explore in order to build up a series of various level of approximations. So if you solve, if psi is actually allowed to be anything in the Hilbert space for n particles, then you have the equivalence between the Schrödinger equation and the variational principle. But the idea is to restrict this variational space to something you can actually do more realistically, and you restrict it to Slater determinants. So states, many-body state of independent particles. You restrict so you solve the variational principle in this subspace, and what you get is the time-dependent Hartree-Fock equations. So that's a series of equations, IH bar d on dt for the single particle state, which make up this Slater determinant. And you have the self-consistent single particle Hartree-Fock Hamiltonian. Self-consistent because it depends on the density, on the state itself. And you have a equation like that. One for each occupied single particle. So that's a much simpler problem than trying to solve Schrödinger exactly, because you just have a series of nonlinear Schrödinger equation for one particle. So you have A of those, and that's something we can do on a computer, much simpler than to try to solve the exact Schrödinger equation, which very quickly will build large set of Slater determinants in your state. Okay, so is there any question about that? That's just what we did yesterday. All clear? One thing I didn't tell you is how so this H here, I told you it comes from the energy density functional. So H alpha beta, matrix element of the matrix H, is obtained from the functional derivative of the energy density functional. So that's an object which tells you how the energy of the system changes with its density. And notice you have to swap the indices. If it's alpha beta here, it's beta alpha here. So just I don't want to spend too much time or to discuss really this object itself, because it's I mean, it's probably an entire course on itself. It's usually fit on structure properties. So for instance, infinite nuclear matter properties, binding energy of few doubly magic nuclei, their radii, things like that. So you will fit a form of this energy density functional, and then you can use it to build your Hartree-Fock Hamiltonian. The good thing usually is you only fit this object on structure properties only, nothing about reactions. And then when you your Hamiltonian is entirely determined by, that's the only input of the theory. So you only used structure information in order to do a calculation, for instance, for the fusion of two nuclei. And I'll show you some example a bit later. So there is, as far as reaction mechanisms are concerned, it's a parameter-free theory, because all the input come from structure. All right? That makes it quite elegant, and also you hope that if the functional is good enough, it's going to be predictive when you go toward exotic nuclei, toward super heavy nuclei, toward astrophysical scenario, and you can use that to look at, for instance, the dynamics of the crust of neutron stars or things like that, something very exotic, hoping that your functional contain all the physics, the reasonable physics. Okay? The one thing I would like to do quickly before I show you how we solve the Schrödinger equation in practice on the computer is to rewrite this set of equations to some different form, which we call a Liouville form. So essentially what so this is for when phi is a vector, h is a matrix. Of course, you can use the Dirac notation and use an operator for h and a ket for phi. And in this notation, we also show that the density. Oh, yeah, no, I didn't show, so I need to do it. The density matrix, a matrix element rho alpha beta, is the expected. So I told you that it's the expectation value of a dagger beta a alpha on any state. So that's quite general. You can use that for any state. It doesn't have to be a Slater. Now, if it is a Slater, it gets simpler. And you can write it as sum from I equal 1 to a. So we showed that yesterday of phi I. I should do it in the right order. So if phi I, the overlap of phi I and alpha, and the overlap of the bra phi I and beta. So we showed that yesterday. So that's only when your state is a Slater. Its one-body density matrix can be written simply like that. So you sum for each single particle the overlap with alpha and the overlap with beta. Now you can define that as alpha rho, an operator beta, and in this case where rho is just the sum over a single particle of phi I, phi I. So you sum the bra and the ket for each occupied single particle. Okay, so that's a one-body density matrix operator. Now, the reason I did that is because now I want to write my Hartree-Fock equation as function of this matrix density rho, not just as function of the phi. So how do I do that? First, I need this equation, and I will also use the Hermitian conjugate of this one. So I'll write it just above. Minus I h bar d on dt of phi I. So that's just, I'm just taking the Hermitian conjugate, so I becomes minus I equal to phi I h h. Now what I do, for both this equation and this equation, I will just multiply by the ket here and by the bra here. So what we have, we multiply, I should have, so for this one you have, you multiply ket by the bra, sorry, and then you, so you do it on the left, you do it on the right. And now you recognize something which looks like the density matrix. You do it the same thing here. So you multiply by phi I here, and you sum over I. So here it's just the density matrix rho. That's what we define here. And here we recognize the density matrix, so we have H times rho. So if you take this equation, this one, let's call it 1, and this one, let's call it 2, and you do 1 minus 2. So you have I H bar sum over I equal 1 to A of d on dt phi I plus phi I d on dt phi I, and on the right hand side I have H rho minus rho H. That's just H rho minus rho H. So you see, I can write that as sum over, sorry, I H bar d on dt of sum over I equal 1 to A of phi I phi I. So I just take the time derivative outside. Yes?
Should on the right, left-hand side, the second term is ket d by dt, should that be a bra?
Yes, thank you. So I just take the time derivative out, I write it like that. So that just I H bar d rho on dt. And what I have on the top is just the commutator of H and rho. So that's a very common form of the Schrödinger of the TDHF equation, and we call that a Liouville form or Liouville von Neumann. One is for classical equation, one is for quantum equation. I never know which one. Probably Maria knows. Anyway, so that's a quite useful form. You can actually write the Schrödinger equation that way as well, with different definition for the density matrix, but you can do it the same. Okay. But in practice, when you try to solve numerically the equation, the TDHF equation, you don't use this form because the density matrices are quite complicated objects. They will be very large matrices at the end. While if you use the form where you have one equation, one nonlinear Schrödinger equation per single particle, it's much more you have much less memory required to store your object. So the density matrix is a very big object, but the wave function for one particle is not very big. So it's actually simpler numerically to use the Schrödinger equation for each single particle. So let's write them in a given. So we have phi I in a grid. So you will have one in a Cartesian grid. So you have a Cartesian coordinate S spin Q, because you can have protons and neutrons. It can be spin up and spin down. And now you have H times phi. It's a product of a matrix times a vector, and when you use a continuous basis, that will give you an integral d3 r dash sum over s prime and q prime. And h of SQ R dash S dash Q dash, and the wave function phi I R dash S dash Q dash. So that's what you will actually put in your computer. So you have one equation per particle. So you can already estimate what will be the size of, say, what you need to store, what memory you need. If you have a grid, if you expand this wave function on a grid, typically you will require, for one nucleus, you can do it with 10 points in X, 10 points in Y, 10 points in Z, with a mesh of, say, half a femtometer up to 1 femtometer. So you can have about 1,000 points for one nucleus, for one wave function. You have A of them. So that will be A times about A times 1,000 points to store the total wave function for one nucleus. You can also, you will have different components for spin up, spin down. Well, usually you have pure proton or pure neutron, so this doesn't add another dimension, but you could eventually have mixture of protons and neutrons in your wave functions. And it's a complex number, so that will be, say, spin up real part, spin down real part, spin up imaginary part, spin down imaginary part. So you will have 4 components per for each single particle. So it's not just such a big object, it's not such a big matrix. You can store that in the computer quite easily. Of course, when you are, we said maximum number of nucleons you can have is when you have 2 nuclei with, say, 2 actinides colliding. It's about 500 wave functions. And in this case, you need a much bigger grid than that, because you have 2 nuclei. So you will have, say, a grid if you are looking at a central collision only, you will probably require, I don't know, up to 100 points here, but that will be really maximum. Maybe 50 here, or 40, whatever. 50 here. Probably Kyle will know. So that will be already a big calculation. You put 2 actinides and you solve that. So you can, you see it's much more than 10 to the 3 now. It's so 500 nucleons and 10 to the whatever. And on the supercomputer, you will, to do the dynamics of that, you will require at least 1 week or 2. So that's give you an idea of how big the calculation can be. But if you are just looking at one nucleus, and you just perturb it and you look at its vibration, that will take you can do that on a laptop for less than 1 hour or so. Okay, so what will be the algorithm? Now, when I say you solve this equation, so how will you actually put it in a computer? The problem here is the self-consistency, the fact that H depends on rho. And because it depends on rho, and you have something which is moving, rho depends on t. So H depends on t as well. It's a time-dependent Hamiltonian. Now, when you have a Hamiltonian which depends on time, you can't use the usual evolution operator to you can't use the usual evolution operator to go from an initial time t0 to a final time t1. That's not possible if H depends on time. So you need to do it in a different way, and the way you do it is, again, iteratively in time. You will just propagate for short time, during which you assume that H is constant. So if you do that for a very short time, you do a propagation for a short time, H doesn't move, then you can use this evolution operator. But then you need to repeat it again and again and again in order to propagate your wave functions. So say you start initially, you have a set of wave function at the time t. First thing you do with that is to calculate the density. And with that, you calculate the Hamiltonian at the time t. Okay? Then you do a first evolution. So you will evolve to get phi I at t plus delta t. If delta t is short enough, you can use it, an evolution operator I should. And then you can say, okay, well, that's good enough. I just do this evolution for a small time, assuming my Hamiltonian to be in t and t plus delta. And then I get a new set of wave function, and then I can iterate. But there is a problem if you do it that way. Do you have any idea of what will be wrong if you do it that way? If you just do that, if you don't do anything more. Think in terms of symmetries. And what you want is a unitary evolution where your number of particles will be conserved, your energy will be conserved. And in order to have conservation of energy, you need, it should not matter if you propagate, you should use the same operator to propagate, say, forward in time or backward in time. Okay, that's micro-reversibility if you want. Now, if you propagate forward in time, you use h of t. Now, if you propagate backward in time, if you reverse this equation, you will use h of t, but on phi of t plus delta t. It's not symmetrical. So you need to find a way to symmetrize that. What you do is to find an estimate of h, not at t, but at t plus delta t on 2, so in the middle of the time interval. If you don't do that, after 100 evolution, your number of particles is going to diverge, your energy is going to diverge, and everything.
Wasn't your argument though that h of t and h of t plus delta t were pretty much the same?
Yeah, but pretty much they will have to change. It's true, but you will accumulate errors very much faster and too quickly, in such a way that because you break ultimately the micro reversibility, you can't ensure that you will have an evolution which is unitary. That's a problem essentially. I get your point. In principle, if t is infinitely small, then it doesn't matter because h didn't change. But eventually, you will accumulate changes. At each small time step, you change your Hamiltonian. So if you do that for say 100 evolutions, the Hamiltonian you will use to propagate forward in time for 100 time step will be different than the one you use to propagate backward in time for 100 time step. And that's what will be responsible to change your number of particles and energy. So anytime you have something, a unitary evolution like that, you propagate something with a unitary operator, you need to make sure that your operator, your algorithm is perfectly symmetric. So you need to find an estimate of h of t plus delta t on 2. So what you do is you do that, and that defines a set of wave functions which you call phi tilde. They are just temporary. With that, you get an estimate of the density at t plus delta t. With that, you take the average of the densities at t plus delta t on 2. That's just rho of t plus rho tilde of t plus delta t on 2. Okay, so now you have an estimate of your density at half the interval. From that, you get a Hamiltonian. From that, you get a new set of wave function, phi I of t plus delta t equal exponential of h t plus delta t on 2 on h bar times the initial wave function. And now you're done. You have a new set of wave function which you can use again and propagate in time iteratively. So believe me, if you don't do this estimate of the Hamiltonian at half the interval, you always have your algorithm will always quickly diverge. Some numerics. In principle, you could even once you get this, you could even improve by using this new wave function. You use it here. So from that you actually estimate a new density, then a new density at half the time interval, then a new Hamiltonian, then you propagate again, and you could loop like that until you have convergence. And once you're happy with what you get, then you can go to the next time step. But that's a bit overkill if you want. Usually, if delta t is small enough, you don't need this shortcut here, this internal loop. But you can prove that you will have an exact convergence. You can prove that you will have a much better convergence if you actually have this internal loops that improves your Hamiltonian and t plus delta t on 2, and then you can do the propagation over time. Is there any question?
Yeah,
oh yes, you have a lot of numerical criteria you can use to estimate the error. You can, well, first thing, you never use an exponential, you always truncate. So it's not fully unitary. So what you will always check is the number of particles, the orthogonality of the single particles, their norm, the conservation of energy, the conservation of angular momentum. As long as your particles do not hit the side of the box, angular momentum should be conserved. So there is all the physical properties which are supposed to be in your Hamiltonian, you should have that.
Do you check step by step?
No, you check at the end of the calculation usually. Well, you see, the way you calculate the Hamiltonian at half the interval is by using this wave function at t plus delta t, which is not very good because you are doing this evolution with h of t. So if you actually, once you get this new set of wave function, you reuse them as phi tilde, then you calculate a new density, a new Hamiltonian, and you do the evolution again, you will actually have a better estimate of this middle density and this middle Hamiltonian, and until convergence, where doing internal evolution doesn't change anymore. And then when you're happy with that, you can go to the next loop. But in practice, you never need that. I mean, I don't know any code which needs that. There's one paper by Flocar in the 80s who were discussing this internal loop, but in practice, you never need it. As long as your time interval is small enough. So typically, a time interval we use will be 0.01 10 minus 22 seconds. That's the sort of time interval you are looking for, very short time interval. So if you don't want to look at the fusion of two nuclei, typically you will need from 1,000 to 10,000 iterations depending on the system. So that can take quite a long time. While we are talking about numerical stuff, when you have a box like that, you need to fix your boundary conditions. So you need, for instance, what people can use is either to use a hard boundary condition. So if you have a nucleus hitting the side of the wall, the side of the box, it just bounces back. And if you do that, of course, your numerics, I mean, the numerics is okay. You solve some problem, but the physical interpretation is completely wrong, right? You don't want to look at what we call the physics of the box. So you need to have box large enough so you don't have interaction of the nuclei with the side of the box. So you can have hard boundary condition where they will bounce back. You can have periodic boundary condition where if you have a nucleus going away, then it comes back on the other way. You can use absorbing boundary condition where you will put an imaginary potential outside of the box, and that will kill the wave function. So you will not conserve the number of particles in this case, but that can still be used to do some physics. So you have a lot of different boundary conditions to use. But if you have a supercomputer big enough, it doesn't matter. You just use a big box, and then you are safe. All the boundary conditions should give you the same result. I think what I'll do now is to show some application on the screen. Need to make sure that your physics doesn't depend on the side of the box. fusion cross-section or kinetic energy of the final fragment or number of particles, whatever observable you are looking at. In principle, you need to make sure that by taking larger boxes, you get the same result. So you need to find like that a size of the box which is small enough so that you can run calculation, and big enough so that it doesn't affect your results. So it's I collected some of TDHF results. So that, you know what, I told you that you always need to start, I mean, initially you need to start with a set of wave function. So what you will start with usually is a Hartree-Fock, static Hartree-Fock. So static Hartree-Fock is just the static version of this equation. It's detailed in the note if you want to look at how we solve Hartree-Fock, a static Hartree-Fock for a ground state of nuclei. You look in the note. I will skip that in the lectures. But essentially what you end up with is a set of, is a nucleus. So it's a Slater determinant which describes the ground state of your nucleus. So you have an example here for oxygen 16, where you have different single particles. So I think I showed only the neutrons here. And what is shown is the density you will find in your grid for the different single particles. And because this nucleus is spherical, you recognize the degeneracy you would have for a spherical nucleus. So 1s 1/2, 1p 3/2, 1p 1/2, and so on. These numbers, these letters and numbers are only valid in principle when you have a spherical symmetry. So if you do a calculation in a Cartesian grid, you don't have spherical symmetry. However, if your nucleus is spherical, you will naturally recognize this pattern of degeneracy. That's an example of a calculation. What you see is actually really the density which comes out of a code, and we are going to play with that. So when you go from that, so you keep in mind that everything I will show will only show one nucleus or two nuclei. But to get what I show is always obtained by summing the densities of each of the single particles. So it's really a unibody problem. And if you sum, say, all these wave functions, all these densities, what you get is something spherical for an oxygen, if your nucleus is spherical. Same way for calcium-40, so you will get a very boring spherical nucleus. But just keep in mind that to get this, you need 40 single particle wave functions with spin up, spin down, isospin, and imaginary part, real part, and so on and so forth. So then you get a boring spherical thing. If you just do Hartree-Fock and you use that in TDHF, nothing is going to move because you're in the ground state. So you need to perturb the ground state. And the way you do that is to apply an excitation. You can put a time-dependent perturbation in your Hamiltonian, or you can apply a boost that's equivalent. For instance, what I will show here is a perturbation where I apply an octuple boost on the nucleus and see what happens. So the nucleus acquires some octuple shapes and vibrate in time with some complicated time evolution. And that's it. So you can plot what, for instance, what the octuple moment is. So you know what is an octuple moment? That will, if you want, measure the triangle shape. An octuple moment is 0 for a sphere, or is 0 for a cigar. But if you have a pair, it's non-zero. So it will measure pair shapes. So when you plot this octuple moment after exciting, you could choose that for quadruple moment, monopole moment, whatever moment you want, okay? So it's just an example. And what you see is that you are oscillating between pair shapes with some complicated pattern. And you can look at the time here. The time scale is zeptoseconds. So you have typically 1 zeptoseconds to do an oscillation. You can try on a piece of paper on the back of the envelope, estimate what will be the energy of such an oscillation, h bar omega. And you will find something of the order of 1 to few MeVs. And that's a typical energy level of vibrational state in nuclei. Okay. So when you get that, you can't do much. Like you just have a time function which is complicated. And so what do you do with that? What is the first thing you do when you have something which oscillates in a complicated way? You what? You integrate the square? Yeah, okay. No, I had something else. When you want to analyze what is vibrating. Sorry? Fourier. You will just do a Fourier transform. Okay? And if you do that, what you get is a set of peaks. And each of these peaks will be corresponding to some excited state in your nucleus. So that's how you will calculate, predict possible vibrational state in the nucleus with TDHF. So you will do that for small vibrations, small amplitude vibration, and in that you probably have heard of RPA, random phase approximation, and that fully equivalent to RPA. And we are going to, it's shown in the notes. This afternoon we are going to do a little bit of exercises on the to show how we go from there to there, and it's how we extract the energies and the collectivity. So the size of the peak here, the area of the peak tells you how collective is the state. So for instance, this is probably just 1 or 2 nucleons contributing. So it's not very collective. While here you have a monster. So you have many nucleons vibrating together. So you can get from that the collectivity and the energy. So this afternoon we will do a little exercise on linear response theory to see how we get these energies and these transition amplitude, from which you can calculate. So if you are a spectroscopist and you are interested in B of E2, B of E3, all this sort of whatever it's called, it's proportional to the area of the peak. So you have formulas, and you can calculate what will be your B of E2 or B of E3. In this case, that will be a B of E3 because it's so small. All these states you see here. So what is the ground state spin and parity of calcium-40? 0 plus. Now you excite them. You excite it with an octupole moment. What are the spin and parity of these peaks? 3 minus. Octupole will transfer 3 unit of angular momentum and will reverse parity. So all these peaks are prediction for 3 minus state in the nucleus. If you start with a quadrupole operator, you will have 2 plus states. If you start with a monopole operator, you will have 0 plus states, and so on. Of course, keep in mind that everything is wrong. Okay, we are not solving Schrödinger exactly. We are solving Hartree-Fock. We have this approximation that we have only a single Slater determinant for state. So there is a lot of physics which you miss, but it's usually for many nuclei you can get some at least a good approximation of what will be the vibrational state with RPA or with this technique. If you look at another nucleus, nickel 56, in this example, you see you have a completely different pattern, much faster oscillations. So if you do the Fourier transform of faster oscillation, what you have is higher energy. Because you have many peaks contributing. So it looks chaotic, but because you have different modes contributing. Some are slow. This one is a slow pattern like that. But this one will be much faster, and they're on top of it, and they are smaller in intensity. So that's why you have this additional oscillation on top of it.
What kind of boost you need? You should maybe tell something.
Yes. I mean, we will, again, that's something that we will see that in this afternoon in the exercises, but I can show you how it works in while I'm writing that, you can think of an explanation why the 3- state for calcium-40 is much lower in energy than the 3- state for nickel-56. So the boost, so you have your initial Hartree-Fock Brown state, and you excite it with something like exponential minus I epsilon and an octuple moment. In this case, it was an octuple operator, so I don't remember the shape of an octuple operator, but if it was a quadruple operator, which induce cigar shape and oblate shapes, you will have a sum for each nucleon. There is a square root of 5/16 pi, and then you will have 2z squared of I minus x . So essentially, you apply this single particle operator to each of the wave function. So that's when you have a wave function like that, and you apply exponential minus I don't know, kx, for instance. That's a boost. What is it? What is it going to do? If I apply this on the wave function, what's going to happen to my function? Just kx, a simple one. Translation. So that's going to induce a momentum to the so translation in momentum. So that essentially you give a momentum h bar k to your wave function. So if you have something sitting here not moving, you apply this, it's going to move in one direction. So that's how we actually boost nuclei to make collisions. That's what we will use. This is just a more complicated form, which instead of moving all the nucleons in one direction, it will move the nucleons in such a way that they will change their shape like that. Okay, induce a cigar shape, for instance, or induce an octuple shape if you use an octuple operator. So why is it higher in energy than this one? Any idea? Magic? Why is 3- state in nickel 56 higher in energy than the lowest 3- state in calcium 40? It's the low-lying octuple mode. They are both doubly magic. They are both N equals Z. I'll help you. That's your calcium 40. And that's the single particle levels which you get from the shell model of Meyer-Goppert-Meyer, but you have the same thing in your Hartree-Fock calculation. So when you want to excite your nucleons and put them to in such a way that you get a 3- state, you start with a 0+ state and you want to end up with a 3- state. For calcium 40, where should I put, for instance, this nucleon? Now? Yes? You put it to F7 half. So what you have is now to couple the angular momentum 3/2 and 7/2. So you know you can go from 7/2 minus 3/2. That's 2. From 2 to 7/2 plus 3/2, which will be 5. So by coupling this, you can have j equal 2, j equal 3, j equal 4, and j equal 5. And now if you look at the parity, well, that would be the product of the parity of the whole times the parity of the particle here. So you have SPD is positive parity, F is negative parity. So you change the parity, the total parity will be negative. So you get 3- by doing that. Okay? And in fact, to get something so collective, I told you there is many nucleons which are contributing. So you don't have only this excitation, you will have also excitation like that, like that. So all of those will contribute coherently. So essentially you have 3, 4, 5, 6, 7, 8, 9, 10, or about 10 nucleons contributing to the vibrational mode you see here. That's why it's such a large peak. Now look at what happened for nickel 56. Where do you go? How can you actually make a 3- state from that? Any guess? You take something from the 2s and you put it where? If you put it here, you will have a minus parity, but then you will not have enough angular momentum. The maximum angular momentum you will get is 2. So I'll show you what you can do is to take a nucleon in 1/2, 7/2, and you need to put it very high in order to actually have a coupling which to 3-. So that's why it's high in energy. There is also another possibility, which is to start from 1d3/2. You take this one and you put it to the 2p3/2. You can couple to 3-, but you see, to do that, you need to cross 2 magic gap for 20 and for 28. So that's a lot of energy. And that's why the 3- state in nickel 56 is predicted at such high energy compared to the calcium. Yes, so if you look in calcium 40, the 3-, I don't know it's the detail of this calculation, but you see it's about 3.54 MeV. And experimentally it's at 3.7 or 3.4, so it's not far. And even if you calculate the area of the peak and translate that into a B of E3, you're correct by about 20% often. So it's not very bad. For the nickel 56, we don't know the state because it's an exotic nucleus. People haven't confirmation of the 3- state in nickel 56. They have a tentative state which is at much lower energy. But again, sometimes it doesn't work. Like sometimes you compare with experiment and it's not the right experimental spectrum you get. And the reason is because you are just looking at a subspace of the Hilbert space, right? For instance, if your states have a lot of clustering, you have alpha clusters and things like that, this is not something you have in an independent particle state. So there is a lot of physics you are missing, but you still get some good idea. And what I really like is, you see, you are looking at an object moving, which basically sum all the internal nucleons, but you can explain everything you see from what you have at the single particle shell structure. And you can even have some stuff like that for reactions as well. It depends on the density functional. Yeah. True. It depends actually a lot, especially for the low-lying states. Not so much for the high energy states. Low-lying, that depends, yeah. Okay, you want to have a break now? Maybe? Yep. Okay, so what we did, the examples I showed so far were for vibrations. Now I'll just show some other applications to collisions mostly. So for a collision, you need to start with 2 nuclei. Okay, you can't do a collision with only 1 nucleus. So that's an example of an initial configuration. So you can recognize Cartesian grid in 3 dimensions, and in the back you have a calcium-40, so the density for calcium-40, and in the front you have a density for uranium-238. So you have, just to explain what you see on this figure, you have two iso densities, one at low densities, that's a yellow surface. Okay, you just see a nice nucleus which can be deformed, or so you have your two nuclei. And there is another iso density, the blue surface, which is at higher density. And you see, you recognize inside the uranium excess of density which are produced because of the population of some shells, which have some torus shapes or whatever. So it's just, I think, a nice illustration to show that also we are looking at densities which are just an average thing. You can still have some internal quantum shell structure appearing, even at something like the densities. So that will be an initial condition, and then what you can do is to boost them. So you will use a boost like that to put a nucleus into motion. So of course you put one boost for one nucleus and one boost for the other nucleus in opposite direction, and you can have some impact parameters if you want, and you can change the energy. So you can do all the initial conditions you want in terms of energy, impact parameter. In this case, this is oxygen on lead, so the nuclei are spherical, but if the nuclei are deformed, you can also change the orientation and see how it affects the reaction mechanisms. So the top one, you see the difference between these two collisions are going to be only 10 keV. So what you see for the first one is what we call a kissing mode, and they don't like each other and they reciprocate. You see the same thing for the bottom one, except that finally they change their mind and they decide to merge. The difference of energy is only 10 keV. So that's how we actually, what we determine what is a fusion barrier. So in this case, the fusion barrier is something between 74.44 MeV and 74.45. It's very precise. And it matches perfectly what you see experimentally. Experimentally, you will have a much broader barrier distribution. So as long as you have an energy density functional which fits properly things like the saturation density and things like that, the barriers are usually well reproduced. Yes. Yeah, well, I'll show some of them. Yeah, I collected. I didn't want to do too much derivation. I did a lot yesterday, so I collected a lot of movies. So now let's try to collide calcium-40 and nickel-56. So that's the same nuclei we looked at the octuple vibration before. Okay. And remember, calcium-40 has a low-lying 3-. Calcium-56 has only a 3- at about 10 MeV, so quite high in energy. So what you would expect is that the 3- will be easily excited for calcium-40 because it's at low energy, but much more difficult to excite in nickel-56. So you collide these two nuclei. The calcium-40 is on the left, the nickel-56 is on the right, and when they start merging, and then they reciprocate, you can recognize the shape here as an octuple shape. So the nucleus, the calcium-40 is vibrating, has an octuple vibration. Maybe you have seen that in the movie, but not the nickel-56. You see? So it's a nice, and it's only due to the fact that you have different energies. So you see that from the densities. Now if you give a bit more energy, so the nuclei fuse. So that's the configuration you get when they fuse. The calcium has a nice octuple shape, not the nickel-56. And that's again because of it's harder to excite an octuple shape in the nickel. So of course this has a big impact on the fusion itself. Without this possibility for the calcium to deform like that, you will need more energy to make it fuse. Because it has such a low-lying collective state, when they get close enough, it will deform, and which will allow the nuclei to touch and then fuse. Without that, you will need more energy, and typically, so that will reduce your barrier energy by 1 or 2 MeV easily, which is not, which is something you can verify experimentally. So at the end, when you are fusing, your ground state of the calcium-40 is a superposition of the 0 plus and the 3 minus. That's why you get this shape. And then the merge. Okay, so another thing, transfer. So you have, you can look at what happened to individual wave functions, yes? You don't keep the identity. As from the initial time, when you start the motion, you are just looking at once later describing your 2 fragments. So you don't keep the identity. When I write that, it's just, here I don't know where, I mean, in principle, I can't tell you that's a calcium here, okay? What I can only tell you, it's a calcium, it's a system with 96 nucleons, okay? That's all. But if I was, I mean, if people who are doing reactions traditionally have been using coupled channel calculations. And in coupled channel, you always keep the identity of the 2 fragments, and you will let them, allow them to vibrate with some collective states and coupling to collective states. And in this case, that's what you will actually use. So it's if you want, it's a language to convince the coupled channel community that these coupling effects are present in microscopic calculations. So now let's look at what could happen to individual wave functions. So on the top left, I mean, each panel is going to show the collision of 2 oxygen 16 just below the barrier. So the 2 nuclei get close and then reseparate. And on top of that, I superpose the density of 1 wave function, one nucleon, okay, one of these phi I here. So for instance, on the top left, I do that for the nucleon which initially here is in S1 half. So I don't know if you see, but a little bit of blue has gone to the left side. So you have some transfer of the wave function from this wave function. Now you can do that with all the wave functions, so 1p3 half. You start with a donut and you end up with 2 croissants. Much better. Now sorry for those who were in Bormio, I already made this joke. That's for the 1p1 half. Of course, when the nucleons are less bound, you transfer much more than when they are well bound. That makes sense. And then, okay, 1p3 half. Now, a word of caution here, when we plot things like that, we are looking at a 1 wave function. But remember that the state of the nucleus is an antisymmetrized many-body state. So you have many, it doesn't make sense to do any physics by looking at 1 single particle wave function. Everything you calculate, every physics you extract, transfer probabilities, for instance, has to be done by looking at the entire nucleus. You have A wave function, so you need to look at the A antisymmetrized single particle wave functions. If you just look at one of them, you can get something wrong. I won't go into the detail today, but essentially, everything you write, everything you want to predict has to be from an observable which looks at all the nucleons. Just looking at one nucleon, like as I did here, makes nice movies, but physics which you can extract is not very clear. Okay? But this being said, we can calculate transfer probabilities properly and then compare with experimental data. And to some extent it worked, but because it's not an exact approach, of course you are missing some physics, like pairing and so on. I will discuss pairing tomorrow. That's another calculation. So we were talking about the possible orientations. So you choose an orientation of the uranium here, which is where you collide with the tip. By the way, this movie was shown on TV, and I was quite proud. Guess what this one is? You started with calcium and uranium. Guess what is this one? Sorry? It's a lead, or nearby a lead. So what you see when you collide nuclei like that, and in particular with the tip of an actinide, you always form a lead, or something in the lead region. So that shows that you have shell effects because you are doing everything starting from a quantum approach, and you have the quantum shells, and the lead is more bound than other nuclei. You know, you have magic shell Z equal 82, and usually you will form a fragment near Z equal 82. Even in TDHF, it's able to capture that. Now, this calculation was made by a PhD student who was doing experiment, and he did calcium on uranium and in his experiment, and he said he was showing he saw me showing these movies, and he said, "Oh, that's cool, I want to do it for my system." And I said, well, you can try, but that's never going to work. TDHF is too simple to be able to extract any physics for these systems, and they will fuse, you won't have any quasi-fission or thing like that. So I was very negative, so he did it, he did the calculation, and then it worked perfectly well. And I was first surprised, in particular to see that such a simple single determinant picture can get the shell effects in the formation of the fragment. I was completely surprised. So, well, he did well, and he published that in PRL. He was happy. So that's another configuration. The first one was for a central collision. This is for with an impact parameter. Again, you form a lead in this case. But you see, now when you have a large box like that, and you let your nuclei having some impact parameter or angular momentum, they can reciprocate at different angle, and you will compare the final angle, the final masses with your experimental data. That's exactly what you can measure, and that's what he did, and that's how you can use this sort of analysis to help you interpret experimental data. That's another calculation, but now you hit the side of the uranium, and in this case you can reach much more compact shapes. And if you reach much more compact shapes, you form sort of a compound nucleus, which will then split into symmetric fragments. That's what you see here. The total calculation here simulates 30 zeptoseconds. So that will take probably 3 weeks on a supercomputer to get. I don't know, maybe you are using different computers. How long will that take in your systems?
I'd say a few weeks.
Yeah, a few weeks is typical. Yeah. So that's why I'm always reluctant when experimentalists ask me, "Can you calculate that stuff for me?" Well, give me a student. That's the heaviest one we did. So a collision of 2 uraniums, and this one I particularly like. Cool. Huh? You didn't. I mean, see, input of the calculation is initial configuration, like orientation, energy, impact parameters. That's all you tell your system, and then you let it evolve. You don't know if they're going to fuse, you don't know if they're going to scatter, you don't know if they're going to make 3 fragments. So that's quite interesting. So this one was a cover of PRL, actually. They like the picture. Another application to deep inelastic collisions. So we are looking here at collision of 2 calcium, but at quite high energy, 128 MeV. The barrier for calcium-calcium is about 50 MeV, 54 MeV. So you are at 2.5 times the barrier energy. It's usually considered that TDHF will fail at these energies. I mean, it was thought at that time, so we tried and to see if it was if modern code in 3 dimensions using modern functional will actually do a good job. So the calculation you are going to see is for different impact parameters, different angular momenta. So for this one, they transfer nucleons, but then they go straight. Here, they transfer nucleons, they do some orbiting before they separate, and this one, they fuse. they form a compound nucleus which keep rotating forever. I mean, as long as you did the calculation. So that's the sort of trajectories the system will do. So you see you have some orbiting. So this is a deep inelastic, this one. Typically, how you will define deep inelastic is lot of transfer. So you see you have transferred a lot of matter between the two nuclei. Orbiting, they will stick together quite a long time before they will separate. And kinetic energy dissipation. So the kinetic energy you started with is much higher than the one you end up with. And that will be what you get also in this case. So that's a deep inelastic. And you can do a lot of comparison with experimental data, and it's working pretty well. The only thing TDHF can't do will be when you look at the distribution of the number of particles in the fragment, you will find distribution which are way too narrow. And I'll come back to this problem if I have time tomorrow, and how we actually solve this problem by going to another theory, which is an extension of TDHF, which incorporates quantum fluctuation in such a way that you can describe the distribution of the number of particles. You can look at fission. So if you start with say you want to look at spontaneous fission of a nucleus, and you start in its ground state, you can put that in TDHF and wait forever. It's never going to fission. There is not enough physics in it. You need to overcome the fission barrier, and you won't have the tunneling of the many-body wave function in TDHF. So what you need to do is to already stretch your nuclei to go outside of the barrier, and then you let them evolve and see what happens to the fragment. So you can do that with different initial configurations and let them evolve. So they're just moving. This one is fermium-258, and you can find some symmetric fragments, asymmetric fragments, and so on. And the thing which is interesting about TDHF in this case is not so much the mass and charge of the fragments, because that you can get from a static approach. You just stretch the nuclei, and what you get at the end will give you the mass and charge. What's interesting here is because it's time dependent, you can you have the fragments moving at the end, and from their motion you can calculate their kinetic energy, and you can predict what will be the kinetic energy of the fragment in a fission process. And that's something which is usually very hard to calculate, and TDHF gives you that in a very nice way. So it works for certain things, not for everything, but for that it works pretty well. So for fermium-58, you will have different possible fission valleys. So a symmetric with compact fragments, symmetric with elongated, and an asymmetric one. So guess why is this one aspherical? Any idea? I'll help you. Fermium has 100 protons. Tin. So you have two tin fragments, and they are nicely spherical because they have the shell effect in the fragments. Well, that was known experimentally, but it's nice to see that the calculation reproduces these sort of things. Of course, here you have tin as well, but because they are deformed, don't have magicity. They are magic. To be magic, they need to be spherical. Okay, so that's my last slide. One main limitation. I mean, there are several limitations, of course. I mentioned the fact that you don't have the width of mass and charge fragment distributions. But another very important limitation is that you don't have a tunneling of a many-body system. So say you are trying to fuse two nuclei at low energy below their fusion barrier. So you know they have two nuclei have a fusion barrier because of the competition between Coulomb repulsion and nuclear attraction. So if you don't give them enough energy, the Coulomb repulsion wins, and then they can't fuse unless they tunnel, they do a quantum tunneling through the barrier. But in TDHF, okay, let's see, what do you need in order to describe this tunneling? You will need to have the possibility for the system to superposition of I have tunneled and a superposition of I have not tunneled. Okay, so the red densities show two oxygen which haven't tunneled, and the blue is when the tunneling occurred. So this final state here, there is no way you can describe that with one Slater determinant. You need two, at least. You need one for the outgoing two fragments and one for the fused system. So why can't I use that in TDHF? Why is it not predicted in TDHF? Yes, you have only one Slater determinant in TDHF. Yeah, exactly. It's outside the Hilbert space of your variational approach. So if you want to describe that, you need to go beyond TDHF. And that's easier to say than to do. Okay? Is there any question about these movies? Oh, yes. If you want to do some calculations yourself, I suggest a code. To my knowledge, there is only one published TDHF code in 3D. And you can look for Sky 3D. So that's not my code, so I can advertise it without any problem. It was written by Joachim Maroon. Not sure if the H is here, or the H might be before the U, I don't know. Anyway, Joachim, if you see me, I apologize. So it's published in computational physics communication or computer physics communication CPC, and that probably was in 2013 or something like that, but I'm not sure. Anyway, if you want to do this sort of simulation, oxygen, you can do that on a laptop. Okay, you don't need 2 weeks of supercomputer. So you can do vibration and light nuclei fusion with on a laptop. You can use this code. It's quite nice. Or if you prefer, I can give you my code as well, but it's not published, so I need to just tell you how to use it. Okay. Now, another request I've had was to tell you about RPA. Or whatever multiple moment. And then I did amplitude of the peak is exactly what I will get in RPA, random phase approximation. So the name random phase approximation refers to some historical way of deriving the equation, which I don't know much of anyway. So don't look for any random phase in what we're going to do. Okay, so it's RPA is the simplest microscopic calculation you can do to calculate vibrational spectra. This afternoon we will look at the linear response theory, which works for any theory, not necessarily for TDHF, and you will see how I got this figure, this spectra, from the linear response theory. Now RPA is a different approach. It's not necessarily time dependent to start with. At the end of the day, it's just an eigenvalue problem, but it's fully equivalent to the linear version of TDHF. So I'll try to discuss a bit of this. I won't go into much detail anyway, so maybe spend just 15 minutes giving you a flavor of how RPA works. Who is going to use RPA? The other lecturer?
I think Barranco is going to use it.
Yep. So that's more like an introduction to this lecture of Barranco. So essentially, if you take the energy versus some deformation. Let's take the quadruple deformation. On this side you are prolate, on this side you are oblate. So if initially you have a spherical nucleus, and you try to deform it, that costs energy. So will, for instance, if you try to make it oblate, that will cost some energy like that. And if you try to make it prolate, that will cost some energy, which can, the figure doesn't have to be symmetric. Usually it costs more energy to have an oblate shape than a prolate shape. That's why you have more prolate nuclei in nature than oblate. Now, when you do that, you see if you, so that's not an harmonic oscillator, clearly. But you can make the approximation that if the vibration only is small in amplitude, then that would be a harmonic oscillation. So you can just fit that, if you want, with a harmonic oscillator. And that will be what you will do in RPA. In RPA, you only look at the small amplitude vibration in the bottom of the well. So that makes this approximation that the potential is just quadratic quite good. So it's an approximation, RPA is an approximation that the potential is quadratic, if you want. Okay? And then if you have an harmonic oscillator, you have a quadratic potential. Well, you all know that the eigenenergy of a harmonic oscillator are just bar omega. And what is omega? Omega is just a curvature here. Okay? So just by looking at the frequency of the oscillation, omega, gives you what will be the eigenenergy in the RPA picture, in the harmonic picture. All right? So, when we did this, calculation where I was trying to find the configurations, which give me a 3-, you will probably have noticed that I took only one nucleon to make my 3-, but I could have taken 2 or 3 or whatever. I took only one. And the reason is because I was doing a calculation which was RPA, and now what I will show you is that RPA construct this vibrational state only by doing one particle, one hole excitation. So taking one nucleon from below the Fermi sea, that makes a hole, putting it above, that makes a particle. So that's why we call that one particle, one hole. Okay? So because we are looking at small amplitude, that means we have our initial state, the Hartree-Fock ground state, which we excite with an exponential -i with a boost, epsilon q. And in a small amplitude, I just want to do a small excitation. If I do a small excitation, I just keep epsilon to be small. Okay? And in fact, RPA is obtained by keeping only the first order in epsilon. Every second order will be neglected. So when I do this boost on the wave function, I change the one-body density. The one-body density will then evolve in time. There will be rho 0, which is the Hartree-Fock density, the one I had at the beginning, the one of the ground state, it's not moving, plus epsilon rho of 1, so that the first order change of the density due to this boost with epsilon. And this is going to be a time-dependent function. And then I have epsilon squared, which I neglect. Okay? Now remember one thing, that the density matrix is sum on I equal 1 to A of phi I, phi I. So we are going to use the property that rho squared is equal to rho, and you'll see that this property will give you particle hole excitations in rho 1 only. So what I mean by rho squared is equal to rho, let's calculate rho squared. See, so I have sum over I and j of phi I, phi j, phi j. Now, of course, phi I, phi j is just delta ij. Okay, it's 0 unless I is equal to j. So this thing is nothing else but my initial one-body density, sum over I of I, phi I. That's rho. So rho squared is equal to rho. Okay. We also say that that's a property of a projector. So if you want, rho is a projector on the subspace of occupied single particle wave functions. That's another way to say it. Fine. So now if you just calculate rho squared and as a function of rho 0 and rho 1, so you have rho 0 squared plus epsilon rho 0 rho 1 plus rho 1 rho 0 and then plus order 2 in epsilon. Okay? And of course, this should be equal to rho, so rho squared is equal to rho. And rho is just rho 0 plus epsilon rho 1 plus order 2. So what we find in the lowest order, so in epsilon, so we see that rho 0 squared is equal to rho 0. That means the Hartree-Fock ground state, that's a one-body density of the Hartree-Fock ground state. So these two things have to be equal. And now for the first order in epsilon, what we find is rho 1 is equal to rho 0, rho 1 plus rho 1, rho 0. Fine. Now what we do is to write matrix in the particle hole space. Let's look at rho 0 and in the basis in which rho 0 is diagonal. That's called the canonical basis. And in this basis, what we have is 1 for the occupied states, which we call whole states, and 0 for the particle states. So that's what my Hartree-Fock ground state one-body density matrix looks like. Now let's write rho 1 in this basis. So we will have rho 1 for whole states. We will have a submatrix rho 1 for particle whole states. A submatrix rho 1 for whole particle. And a submatrix rho 1 for particle. Fine, now you use this. You use rho 1 equal rho 0, rho 1 plus rho 1, rho 0. So I just let you calculate the product of this matrix times this matrix, plus this matrix times this matrix. And what you get, you will get you should get something which is 2 times rho h prime, so the whole part of rho 1, 0 for the particle part, and then you will have the particle whole part and the whole particle part. Now this should be equal to rho 1. Okay, that's what I wrote here. This product of this matrix, which I've obtained by multiplying these two, should be equal to rho 1. Now that tells me that rho pp has to be 0. So there is no particle elements of rho 1. Now what about the whole part? You have something equal twice the same thing. What does it mean for this something? It's 0. So both are 0. So the only thing which you have in rho 1 are particle whole and whole particle. So these one are not 0. So when you do RPA, you are essentially looking at this quantity, rho 1, and you see it only considers particle whole and whole particle states. So that's why RPA only contains particle whole excitations. One particle, one whole excitation. And that's why in this picture, what I did on the board, I was only promoting one nucleon because I want to compare with RPA. Now in nature, you can have more than one particle promoted above the Fermi surface. You can have 2 particles, 2 whole. That's not in the RPA basis. And that will, for instance, you will need to go to the second RPA in order to incorporate these states. I probably ran out of time. Did I? Is there a quick thing I wanted to do? Yeah, shall we stop here or it's fine? 5 minutes? Okay, let's try. So, yeah, okay, quick. So what I will get to is the RPA equation now. Now, what I just showed you is RPA as describe a one-body density matrix which has only particle whole excitations. Now what I will do is to start from the TDHF equation, keep only the first order in epsilon, and from that we will get RPA. So let's start with the TDHF equation. I h bar d rho on dt. So I'm using the Liouville form equal to the commutator of h and rho. So that's TDHF, and now I'm only keeping the first order in epsilon. So I have rho equal to rho 0 plus epsilon rho 1. So that's equal to h of rho 0 plus epsilon rho 1. So that's h is a function of this density. Commutator with rho 0 plus epsilon rho 1. Now I develop and I keep only the first order in epsilon. First, remember that this is static. Okay, that's just a Hartree-Fock ground state. So the time derivative of a constant is 0. And that, what do I have on the right? So this, I need to do a bit of work, and I'll write it as h of rho 0 plus epsilon a term epsilon which I write as a functional derivative of h with respect to rho. And in fact, what I mean by that is a shorthand notation for all the possible variation of h with variation of all possible matrix element of rho 1. So delta h on delta rho is a sum over all the particle hole, because rho 1 has only particle hole, of delta h on delta rho h need to make sure I'm not keeping the indices correct. Yes, some pH rho 1 pH, and that's evaluated at rho equal rho 0. That's for the particle hole, and I have the same term for the whole particle, delta H over delta rho whole particle, evaluated at rho 0 times rho 1 whole particle. So it's just a short, this is just a short notation for this sum, okay? That's a variation of H with each matrix element rho. Now once you do that, and you see that you keep only the first order in epsilon, so what you get is I h bar d on dt of rho 1 equal to the commutator of h rho naught with rho naught is 0. That's a Hartree-Fock equation. So I keep only the first order in epsilon. So what do I have? I have delta h on delta rho times rho 0 plus h of rho 0 times rho 1. So this is essentially the RPA equation, because you have also ordered 2 in epsilon. So anyway, so that's a RPA equation. That's the equation for only the matrix rho 1. So you often see it written as something like that, M applied on rho 1. So M is the RPA matrix. And this matrix, you see, it's when it acts on an object, it's just delta H on delta rho. What did I do? I forgot one thing, delta H on delta rho. I should have multiplied here by rho 1. So there is a rho 1 here. And that's the commutator. I was going too fast, sorry. So in the note it's correct. So you have the commutator of delta H on delta rho 1 with rho naught. So M is just changing rho 1 into this object here. It's called the RPA matrix. This is a Hartree-Fock ground state Hamiltonian. If you just have that, if you don't have this term, you don't take into account the possibility for the change of the state to change the Hamiltonian. And if you don't do that, you don't have any collectivity. You will just look at the oscillation of one particle at a time independently. However, in this term, that's a RPA residual interaction. So you see that tells you how the Hamiltonian changes when you change the density. So what happens if you change the state of a nucleon? That will change H via this residual interaction, which could eventually change other nucleons. And if you find a frequency for which all the nucleons are happy to be excited, you will have the collective vibrations. All right? So if you were, when I was plotting this RPA strength function like that, on the slide before. If you were doing it without this term, you will not have this big collective state. You will just have small states at some energy, at some random energy. RPA is collecting all the nucleons together thanks to this residual interaction and allows them to move collectively. All right? Well, that's enough for this morning.